talk. Hello? Hello? Oh, hello?
No, it's not. It's not on my computer.
A speaker should be this
Yeah,
microphone.
no.
Right?
If you go to the preferences on the more no. No.
To the sound. Hello? Hello? Hello?
I am sharing the screen. Okay. No, I'm not sharing anymore. I just stopped sharing. Now I can start again. Good. Yeah.
And if you start speaking,
1 2 1 2.
it's fine, I think. Can you check the YouTube, Prof? It's good. It's good. That doesn't matter because you never see your own video. It's fine.
Now it's working.
It's okay. Yes.
Okay, sorry for the small technical problem. let's start with the last lecture from today, and then we have the company short talk from IMS and the student talks. And then I remind we have the group picture at the very end, like after the last student talk. So please, Philippe.
Okay, so welcome back on matter wave quantum sensors. In this third lecture, I will start to review specifically some applications of those sensors, and that will mostly focus on atom gravimeters and atom accelerometers, basically. So the first application that I was speaking about was our capability with these sensors to measure gravity very precisely. Remember, about like 1 part per 1,000 from the variation that are induced by tides. So that's very precise, corresponding to something close to a few millimeters of change of height. And so there is a very high interest in knowing very well what we call our geoid. So it's the map of gravity around the Earth. So just a reminder of some of the gravimeter I showed. That's the one that have been developed and used over the past 2 decades. There are a little more here. That's the Stanford gravimeter. I will not come back on this one. That's the mobile gravimeter. That's the one that was developed at Sett. Mobile because there are wheels under the optical table, basically. That's this small version from AOSense, another big mobile gravimeter. So again, they are lab gravimeters. They are operated by students, but they are able to be like transported in some places. There were some gradiometers developed in Italy. So just to say, Europe is actually a pretty good place for this type of sensors with the US. Of course, now if you go to China, they have many very nice experiments on that, on these systems as well. So what is the equivalent that you can use today instead of using matter waves for this type of sensors? And so what is basically the competitor for a gravimeter, for a matter wave, commercial matter wave gravimeter? It's basically on almost the same principle. It's using a laser and a free-falling object, and it's measuring the position of the free-falling object in time in order to record the acceleration. Except that the free-falling object is a real object. It's a corner cube. Oh, yeah. It's a corner cube right there. So you're building an interferometer with one of the mirror. So it's like a Michelson interferometer. On one arm, you have a mirror, which is a falling corner cube. When the corner cube is changing, the length of this arm is changing, and you see fringes, and you measure the fringes. And if you count the fringes, then you know exactly what is the position of your object. So the principle is very similar, except that here you record the fringes with an external photodiode, whereas in some sense, the atoms are recording the fringes themselves while they're falling down, and then you just read the information from the atoms. So that's the first difference. The second difference is that here you drop a mirror, which means that when the operation is done, you have to take the mirror back to the top and redo the experiment. And it's much harder to put a mirror back to the top than to reload atoms from a mod. So which means that in this case, first of all, you have moving parts. Second of all, it ages because the mirror itself, it drops down and up and down and up. At some point, you have to change it. And secondly, you have vibrations because you cannot avoid vibrations when you drop something. And so that's some kind of strong limit of this type of system, but it's a very good system. The performance are about the microgal level, 10 to the -9 G, and it's absolute because, again, the only thing you need to know is basically the laser wavelengths, more or less. But in order to operate that, you need someone who comes and realigns the system, and if you move it, you have to wait because you have thermal variations and etc. So it's not very practical for moving. But that's basically the the reference we were using in order to compare the performances. So that's one reference, and that's what we call what's called in this graph the FG5. FG5 for falling corner cube gravimeter, 05 because it's the serial number of the system, and there are many of those available in labs. So this is the upper trace. The middle trace is a quantum gravimeter using matter waves. And then what you have, it's the bottom trace is some system where instead of dropping a mirror and then measuring the position of the mirror, you're basically levitating an object. In this case, it's a sphere, which is at a very low temperature, cryogenic temperatures. And then you measure the force that you need to levitate, and it's levitated by electrostatic forces. And by measuring this force, you know what is gravity as well. These three objects have about the same level of performance. This is what you see here. This is what you see when you look at the curve, for example, at this level. This is the typical noise you have around the model, which is well known, as I said before. If you integrate, they're about as good. Actually, the superconducting gravimeter can be a little bit better because you can push the sensitivity. But if you stop working with your superconducting gravimeter and then you move it again, then you have to refill it with liquid helium and etc. And then you don't know what you're measuring. So you have to recalibrate, usually with a falling corner cube. So that tells you that today we have competing technologies. The atoms are about as good as the other ones. Now you can tell me, so they were recorded at the same place at the same time. That's the graph, are not just a superposition of different graphs. It's really three measurements done with three objects in the same lab. And now you were telling me, yes, but your matter wave gravimeter here did not work. There is plenty of noise, and that's crap. So I can zoom in a little bit there. And actually, the noise looks kind of a nice sinusoidal signal. It is a waveform, something that you cannot resolve with the falling corner cube system because the time it takes to drop the mirror and then to bring it back and then to wait for the system to relax in order not to have vibrations is actually reducing the duty cycle of measurement with respect to what you can do with atoms, because with atoms, you just create your MOT. It takes maybe 100 milliseconds or 1 second. And then you get to do the measurement and you can immediately reload some atoms. So that's why we have this resolution here. So what is it? Do you have a guess of what's this noise? Maybe someone running around the system. It's actually a more fundamental aspect or something. Well, it's some fundamental in a sense. That's actually an earthquake. Not an earthquake. So these measurements were done in Paris, and it's not an earthquake that happened in Paris. It's an earthquake that happened in China, but that was measured in Paris. So if you do say, so if you look at seismic waves, they are called waves because they actually travel along the crust at the speed of sound. So if you have an earthquake somewhere, then you have a seismic wave which will travel, and actually it can make like 1, 2, 3 turns before it damps. Of course, it will damp eventually, but you can actually, so everywhere you are on Earth, you can record things that happen everywhere. It's just a question of how sensitive you can be. And that's a proof that geodesy or geophysics is actually something that helps you learn a lot about these kind of things. Just for the story, so you could do that with seismometers, and this is why the Americans know that North Korea is doing some test of like some nuclear bomb test at some point. It's because they record earthquakes that are not earthquakes, and they don't need to be in North Korea to do that. Yes? No, it was afterwards for this one. Now we know, but yes. It has characteristic frequency. It doesn't look like noise when you look at that. It's a typical frequency, and then of course you look at this noise, you try to understand, and then you look at this typical frequency, and then you realize it looks like a seismic wave. It has the typical frequency that propagates, and then you make the calculation right, and you find that the time it happens, it makes sense with when the earthquake happened. I will show some other graphs on that. Yeah. So, well, let's say with only one gravimeter here, we just knew that there was an earthquake. So now, if you want to know, it's like a GPS. I mean, you have waves propagating from sources, and you can do time delay measurements. And if you have a network of gravimeter or a network of seismometer, you can actually pinpoint when the source is. Well, because there is a global recording of earthquake worldwide, so you can. Yeah. Yeah, no, you try to understand if it's a problem with the instrument, then you realize that it looks too nice to be a problem with the instrument, then you say maybe it's an earthquake, that you look at earthquake, and then you do the calculation, and you find that it looks like the proper thing. The first time you do that, it's the way it happens. Well, yeah. So it could have been like a train passing by or something. But basically, there will also be seismic waves with also some typical frequency. There are typical frequency that corresponds to traffic, some other that so you can look at that, of course. But in this case, it's also just that first, that was something that was fast enough that you could not see with the other gravimeters. Then you can check that there was not like a big truck passing by the laboratory. It's a very short time, and it's a very single event, so that's the thing. But as I will show later, then once you know that you can do that, you can actually be a little bit more clean about your analysis. So the way you want to, yes? Uh-huh. This I have to double check. I don't remember. But so typically for our atom interferometer, we make a point like 10 points per second, and for a falling corner cube, it's more like 1 point every 10 seconds. That's the rule of thumb. And then it operates all the time if you want. In this case, it can run for days, for months without being stopped. In both cases. Yes, this is the time, not in seconds. That's the time. That's typical. So this, sorry, this is hours because. Oops, sorry. Yes, this is. So I don't remember what's the abscissa, but what I can tell you is this is 1 day. This is 1 day. So one because that's the tidal effect. So maybe no, I think it's days there. So it's yes, between 98 and 300, it's 2 days. So the scale is days. So you can make comparisons, and this is an example of if you want to test and compare your sensors. So this was done in Paris at some reference points. So these GR points are, so there is a room and there are points that corresponds to, in this case, to some pillars where the seismic noise is the smallest one. And then you put one gravimeter on one pillar, the other one on the other pillar, and then you rotate that and you integrate and you look at their level of sensitivity. And this is how you calibrate or cross-calibrate your systems. And that, again, that's how you do metrology with your sensors. And this is, again, a comparison between a falling corner cube, superconducting, and the cold atom system. As you see, the accuracy is about the same, not quite as good, but we can improve that. And the sensitivity is actually a little bit better. And again, the stability is also about the same. So we are competitive with the system, and these are all data, so it has been improved since then. So we are at about the same level. We are not much better. Let's be honest. So we are not much better than a falling corner cube, and we are not much better to some extent from a superconducting gravimeter. But for a superconducting gravimeter, you can be actually much more sensitive, but if you move it, then you have to recalibrate it, which means you need a falling corner cube or an atom interferometer to calibrate it. And if you use your falling corner cube, after a while it stops because all these mechanical parts, you need more maintenance. And as I showed before, the duty cycle is not as good, so you're missing some signal. So it has some advantage. That's the proof of that. So that's some data I showed already. I will not come back on that, but just so that's another earthquake. Now that you know that you can look at earthquake, you can actually have a better look and really focus and say, okay, there is an earthquake. Let's look at the signal we were recording if we find an earthquake. So this is a typical signal of an earthquake here. And that's a typical other one. So they have typical frequencies, as you can see. That corresponds to the typical frequency that can propagate over the Earth. And I'm not sure on this one, or maybe on the other one, no. And you can see sometimes even like a first round and a second round of these traveling seismic waves. I'm showing that for a couple of reasons. First, because it shows one advantage, as I said, because you can really record that. Second, maybe you were not aware of the fact that seismic waves travel all over the place. And third, because I will address later on some other applications for large detectors for gravitational wave detection at low frequency. And actually, this is a very important part, the knowledge of what's happening on the ground and how seismic waves propagate, how sound waves propagate in this media is actually crucial in order to understand that your Earth is actually moving all the time, and that you have to understand that because it corresponds to a gravitational signal or an acceleration signal. Okay, oh no, okay, so that was the one where you have a first burst from and then it rotates, and then you have a second burst. So it takes about half an hour to turn around the Earth. So one of the things that's fascinating with that is what if, and again, it's a big what if because it's purely hypothetical, but what if there are some precursors of earthquakes? If you have a big earthquake, like 7.3 is a rather big one, maybe just before that, you have small signals because your plates are moving a little bit. And that if you understand these small signals, you can actually predict a larger one. And if you can predict a large earthquake, then you can save lives. So that's a big challenge. If you talk to geophysicists, it's a real what if. I mean, it's purely hypothetical. There are two reasons for that. Is you don't have so many large earthquakes in order to make statistics, and you don't want so many. And there not so many network of sensors are available to do this type of search. So if you want to get more data and learn more, you need to have more sensitive system that can actually look at these events for small earthquakes. And I recall that the Richter scale is like a super logarithmic scale. It's like between 5 and 6. There is like orders of magnitude difference in the amplitude. So you want a small earthquake, you need to increase your sensitivity by a lot. And that's a challenge for our system. So that's one potential application of this sensor. Instead of, and it's not completely gravimetry, it's now because you're looking at basically velocity changes. It's more like seismometry or seismology. Let's go back to the real gravimetric stuff. So here you want to measure gravity and you want to make a map of gravity. This is a a picture of this superconducting gravimeter. Yes, I mentioned before. This is a picture of the classical falling corner cube gravimeters. So as you can see, there are many different types of sensors. Some are small scale that you can move everywhere. They are not very sensitive, but they can be movable. Some are big, but they have to stay at some place. And the challenge is to make something which can be very sensitive and that can be moved easily. So what is the motivation for that? So when I was starting to speak about that a long time ago, maybe it's a French private joke, but in the 70s, you know, there was this oil crisis in the 70s, and France doesn't have much oil, and every good way to find oil was important. And some people came with an idea, say, let's have planes that can, and they were calling them the sniffing planes, you know, and can sniff where there is some oil without needing to dig in. Well, that was a big scandal, a political scandal, by the way. But actually, we are building a sniffing device. That's what we want to do now with that. A sniffing device that will actually be able to record if there is a change in density on the ground. And by looking at this change in density, we can infer that there might be some resources on the ground without the need to dig in. So you can then pinpoint where you can dig, and then you have to confirm that it's indeed some oil or something else. So why can you do that with a gravimeter? Simply because the gravitational force, the one that holds you on the ground, that's because you have the gravitational attraction of all the mass that is below your feet. Basically, if you have less density, you feel lighter, and if you are more density, you feel heavier. Except that the variation will be microgal, so 10 to the minus 8 meters per second square. So 1 part in 10 to the minus 8, we cannot really feel it. I would love to, but that's what we want to do. So we want to basically walk and feel whether the weight of our proof mass is changing, and from that make a map. Yes? Yes, it's an integral over everything that you're looking at. Exactly. Yeah. Well, I would not say it like that. I mean, so all the questions is how deep can you look at with a gravity sensor, and what is your spatial resolution? So I will try to go on with what I say, and then we can discuss after. I'm trying to maybe not make a statement, but at least trying to explain that. Yeah, so that's what we want to do. So just to give you some numbers again. So we want to look at small variations. As I said before, we want to be in the regime of nanogravity, 10 to the minus G or 1 microgal. So this changes is of the order a few microgals, and so there are two things: a microgal that's 10 to the minus 9 of the Earth's gravity, and that corresponds to some heights that are of the order of a few millimeters of change. And yes, so you have to so you have to understand now, if you're making a map, whether it's a density variation, whether it's a height that changes by a few millimeters, and et cetera, and et cetera. And that's all the tricks of geophysics and geodesy mapping. But it's a field of application where you have plenty of type of instruments. That's a list of typical instruments. Most of them were what we called relative gravimeters. That means that you take a gravimeter here, move it there, and then you will have a differential gravity between these 2 points, but you don't know exactly what gravity you're measuring. And you have absolute gravimeters that will actually measure, and when you have a measurement, you know that it's actually what you are trying to measure. That's the typical application, and that's the accuracy target. So that's exactly what you're telling me. I mean, it's if I want to have the good resolution to make prospection in microgravity, I need to have an accuracy target on the level of the microgal or something like that. If I'm not as accurate, I will not be able to do the proper maps. And if I'm more accurate, then I will have a much better spatial resolution. And if you want to look at Earth dynamics, it's a few orders of magnitude below that, and etc. So your question is, how can I see underground with a gravimeter? So what's commonly used to do that, it's a plane in which you put a gravity sensor on board the plane. So the way you do is you travel, and as you're completely right, it's each point that you measure is basically a contribution of everything that you have below. But the thing is, you can have some kind of analogy with what you would do with optics. You have a detector which is picking up some light, and it's picking up some light that comes from all the sources around you, or electromagnetism. You have you're calculating the electric field somewhere, and it's the sum of all the sources around you, which means that at each point you have an information, a global information about your distribution of mass. So now you need to be able to retrieve that, which means that you make a map of this, and by making a map, you're eventually able to pinpoint positions of mass, and you can resolve the mass distribution, you can resolve the position distribution, and eventually also the depth distribution. So I have a stupid example, very basic, to show how that can work. It's simpler this way. So I put my detector like this, and I put a mass on the top. This is something we can do actually on an experiment I will present later on. And then I say, okay, I have a point source gravity. So let's say I'm in an empty space and I just have one point source somewhere. So this is the gravity force that the gravity that this point source will create. And then I put an array of gravity detectors along a line like that. So this is, if I make a 2D map of this gravity, this is my source here. And then of course, you know that it's decreasing. Oops, sorry. It's decreasing, and at each point here, you will have a certain signature of gravity that corresponds to the distance from the point. And that's the only thing you can do. So let's do that, and then let's measure not the gravity field, but the gravity gradient. It's just the derivative. So if I take a 1 ton mass at 5 meters from my array of detectors like that, then I can find a gravity gradient, which is of the order of a microgal amplitude, maximum amplitude, and it's 510 to the minus 10 meters per second squared per meters. It's a gradient here. And I have a signature. No, it has a shape. And it's like a point source response of my system. If I'm further away from my detector, this will be wider. If I'm closer, this will be sharper. The amplitude changes the height. The width of my peak is giving me information of where it is away from my array. And then, of course, the position on the array tells me where it is on the position on the array. So this replies to your question, because now I have an analysis which is exactly similar to how I define basically a CCD camera. I have the point source response of my camera, which tells me how systems would reply. And then from that, I can infer exactly the distribution. So it's a little bit more complex here because you have a 3D that can translate in 2D, and you have to be very cautious and you have to have some knowledge. But that's exactly how it works. So of course, it's not that simple because you're not having a point source somewhere in the vacuum, and there is a wide distribution of all kind of things around you, and you have rocks, and you have underwater reservoirs and sand over there, and etc. So you need to have like multiple levels of information if you want to be able to pinpoint, for example, a resource somewhere. So that's why the geophysics application requires more than simply a plane traveling by or just like a gravimeter on the ground. And so you have all these levels of detectors. It comes from space and it goes to ground. And each of them is important and useful for using gravity as like a reference for prospection or other things. If you are far away, you will have a very poor resolution. So you will look at the global average gravity variations, and that will give you some information about what's very deep in your system, like the raw distribution of mass of Earth. And the closer you come, the better your resolution will be, and so the better you will be able to actually have a precision map about what's close to the surface. And so with that, you make some what in the jargon of geophysicists they called anomaly extraction. So you're trying to look at an anomaly, and the anomaly can be a resource hidden somewhere, by starting from the global picture, which is a big average, removing that, and then removing other effects, and then removing other effects, and other effects that you know, until you actually reach a level where you're only left with something that you don't know, and that's where you can expect to have some resources. Of course, it's not 100% certain, but I mean, even digging in the completely blind is even worse than that. So it improves our knowledge. That's and all these points are very important. And as I mentioned, there are some systems what you put as networks. There are some space missions for that. There is a need for these large gravity maps, and then you have like more detailed map using plane or boats and everything. And that's the typical applications also. So that's the typical scales that, so sorry, it's a French one. I used to have an English one, but I don't know where it is. So that's the precision you require and the resolution you're looking at. And that's what you can look at, or that's the typical applications you can check. So that's, so if you are with a very low resolution and a very low precision, you're typically in the top here. And here you're looking at the global variation of Earth. That can be Earth tides, that can be ocean loading, that can be tectonic movements, and etc. So you will have a global information about the system. If the ice is melting in the Antarctica, you can see it with that. And then if you go to lower resolution and very high precision, then you can have what they call salt domes. So that's a small structure underground in which you used to have water, or you still have some water, and there are also some. And in between, you have all kinds of applications. Like this is a glacier survey. This is a volcano survey. This is in this type of applications, you can try to like also predict whether there will be an eruption by just looking at the mass movement in the volcano, and that will give you information about how much magma is coming, because magma is very dense. And at this low level and resolution, you also have all these prospection activities where you can really look at that. So that's gives you, and we are trying to be, milligal. So we are typically we can sit there. So we are in this regime with our system. So that's where we expect to be. So just to give you mass picture, this is and there are even so you can buy a map, but not with roads. You can, or it's not a topological map. It's a geophysics map. It's a gravity map. So you can have this map, and it tells you, if you're sitting somewhere, it tells you how much gravity is right there. And you can buy a map with different type of resolution. And that's very important. It has different use. So as I said before, it can be used to extract information, global information about gravity, and look at anomaly that can be a proof of a cavity or a resource or something else. But basically, it's a map. So it tells you also that if you're traveling somewhere and you're able to measure gravity, you can actually use the map of gravity and your measurement of gravity to tell you where you are. And this is actually a big application for navigation. So a few examples of what's been done. So this is how it was done before. So this is the instrument that flies in planes like this one or helicopters close to the ground, about a few hundred meters above ground. And you do a map with this type of sensor. And this is very old technology. It's actually Second World War technology, which has been improved, but which works very, very well. And if you use atom interferometers in a plane like that, you can improve by a factor 10 or a factor 100. This is maybe a first experiment that was done at Stanford University in a truck. So in this truck, there is an atomic gradiometer. And by just moving the truck and measuring the gravity gradient and recording it, you can find that there is a wall there. So that's the signature of the wall. That's the change of gravity from the wall. And so the wall is not a kilogram, but it's not very heavy. It's not super dense. And you can still see the signature of the wall simply by looking at this gradiometer. So that tells you that you can actually have signatures of structures with this type of system. There were proof of principle demonstration, but they were already very powerful, even though the instruments were not quite commercial yet. This is the most advanced data that you can get now in publications from cartography with a gravimetric system. So this is a onboard gravimeter. You can have a hint of the gravimeter over there. So in this case, it's a big gravimeter which is put on a special platform to avoid the vibrations and etc. And they put it on a boat and in a plane, and they made maps. And so they really proved that you can actually, with the current technology we can achieve, with the current sensitivity we can achieve with this type of system, even on board, we can make maps that are at the level of the maps you can do with other existing instruments. And again, here it was like a survey that was an experimental survey that was paid by the French Department of Defense. And that's really, the application is really underground gravity maps for navigation. There is another type of interesting application in this type of instrument. Again, what's nice with this is you can look at mass distribution and mass evolution without having to drill, without having to perturb the system. So it's good for prospection. It's good for maps and navigation. I'll come back on the navigation case later on. But there is also some important things that you can use for that. And one of the, again, maybe you will be surprised, but one of the mystery maybe not, but it is since not very accurate assessment about how efficient the filling of the water reservoir is from the rain. And it's actually much less efficient than we expect, because there are many phases. You know, the water falls on the ground and then it saturates. And I know it's very well known for Vienna, because Vienna used to be a swamp. So it saturates the surface. It's called the epikarst. And that's the first thing it does. A lot of the water just stay there. And then you lose that by evaporation. And then it will slowly actually move. It will slowly migrate underground. And it really depends on what type of material, what type of rock. It will slowly migrate towards the water reservoir that you rely on basically for your current water. And this is very important to understand. I mean, it's for ecology, it's important, because you can say lots of stupid things about the fact that, oh, it's not raining, we won't have any water. And sometimes it's not raining for months and you still have a lot of water. And sometimes it's raining like hell and your reservoirs are not filled enough. And this is because you need to understand how this water cycle is moving. But it's very hard to do because you very rarely you have access to the water reservoir, except maybe by drilling, but it's very rare because they are currently quite far deep inside and they are just like filling up rivers and everything. So what you can do is you can use, again, gravimeters, and by making a differential measurement between two gravimeters, one at the surface and one below, you can actually look at the ground loading of water from the surface, and then you can look at the gravimetric signature of mass transfer from the surface to the ground. And this is current studies from geophysicists. It's a very hot topic. And actually, in this case, you need a very good gravimeter, sensitive, but also long-term stable. And that's a very good application for matter wave sensors. So that's some data, you know, in this case, you look at the gravity variation. That's what you can see here. And then you try to correlate that with information about the rain. So this is basically the daily discharge. It's the daily rain. And then you find indeed that you have changes of gravity that are highly correlated with rain. So that's the preliminary data. It's not my data, it's data from geophysicists. Okay, so as I said before, I will not talk too much about that in terms of applications, but one of the challenge today is really also to use this capacity of being very sensitive and very stable for enhancing our global knowledge of gravity. So this is one example of a scenario which is currently studied and also supported by the European Union, is to make a gravity mission in space, so a geodesy mission in space using quantum sensors for the stability. One possible scenario is this one when you, so it's also, so currently, how do you map gravity in space? One way is to have one satellite and then measure acceleration. But the other way is to have one or more satellites and just look at their trajectories. Because they have very small drag, or you can know the drag, then by just looking at the trajectory, you basically have an orbit which will be corrected by the small variations of gravity. And this is the way it's done. Of course, it's so tiny that it's hard to do by itself from ground to space. So if you take two satellites and you just record how they move with respect to each other, so basically then you're recorded this perturbation of their geodetic trajectories. And this gives you information about the gravity map, and it's very precise. What you can do with, if you add an accelerometer is really correct for all the spurious noise that the satellite can have. And then if you have the good stability, you can really improve your measurement. It's something we studied with the French and the German Space Agency, and we actually convinced ourselves that we can really improve the current missions by using quantum sensors. So that's one aspect of the applications. I want to switch to another aspect, which is more towards large-scale structures, and basically the aim or the first motivation for this type of experiment was the detection of gravitational wave, which is basically trying to look at space-time perturbation and how you can monitor that with a quantum sensor. So you all know gravitational waves. They are perturbation of space-time. They are very, very strong, but very, very far away. Usually when two black hole collides or when two neutron stars merge together. And on Earth, this very, very strong perturbation is very, very weak. And it corresponds to what we call a strain modulation, so a variation equivalent to a distance, like you would see yourself shrink or dilate by something like 10 to the minus 20 in relative length, so it's super tiny. So usually, in order to monitor space-time or to detect gravitational waves, what you need to do is to look at how light, well, actually how the time travel of light will be affected between two inertial references. And that's how you can actually look at the modification of space-time. So it's either a contraction of space or a contraction of time. You cannot really make a difference. But for that, you need to be sure that you have some reference points that are inertial references. So they have to be free-falling objects, basically. So this is how the gravitational wave detector have been built. You have some free-falling objects. It's the same objects as the one you use for the free-falling gravimeter. There are mirrors, and they are free-falling. I will come back on that because I'm sure you don't agree with that. But and then in between these free-falling mirrors, you're actually measuring the distance with a laser. And by just doing some interferometric measurement, like a Michelson interferometer, you compare the distance between the two arms. So it's very similar to the falling corner cube gravimeter. What's nice is usually a gravitational wave passing by, it has a polarization so that one arm is contracted while the other one is in quadrature, so that you really have a very strong signal when you look at it. So the mirror is free falling, but it's not falling. And that's the key element of these detectors. There are many other key elements, but that's one of them. You want to keep the experiment running for a very long time, so you cannot drop the mirror and then keep it back. So you need to hold it against gravity. So you need to have a suspension that will isolate your mirror from the ground. It has a resonant frequency, this suspension. And below the resonant frequency, you're basically not efficient at all, so you pick up all kinds of things. And above the resonant frequency, the equation of motion of your mirror is considered as a free-falling object. It's exactly the same. It's a pendulum equation. So what it tells you in this case is that, so you have a free-falling object at high frequency, no noise at low frequency, because then your damping works well, but then you have a cutoff frequency, which is this frequency where it's basically cutting off the noise in order to have this free-falling aspect. And typically, if you look at the typical frequency, if you want a cutoff frequency at 10 Hertz for a mechanical pendulum, that's already heights of tens of meters. So it's a macroscopic object, and there is no chance to change it. So there is a fundamental aspect in this type of instrument is they will be naturally limited for very low frequency to your capacity to make a very good pendulum. And they have like super duper suspensions. They are super nice. Huh? They have a damping of extremely good. They are almost isolated. And above this frequency, you really can consider that the mirror is completely disconnected from the ground, but you have this cutoff frequency. So it's very good. They were able to see some gravitational wave, and this is the typical modulation you can expect from that. But it's in a frequency band which is typically 100 Hertz or something like that. So the challenge, now that we know that gravitational wave exists, is to look at gravitational waves in all frequency bands, because we know that at high frequency, you will see certain objects like small black holes, maybe neutron stars. If you go to much lower frequency, you can see bigger objects, but you can also look at events way before actually the final collapse happens. If I go back to this curve, it's not, so it's amplifying a little bit here, but it's also, the signal is also reduced by the fact that the bandwidth of your system is not good enough. So it's the sensitivity function of your instrument, as I introduced before. At lower frequency, it's 0, so you don't see anything. But if you had a good instrument at low frequency, you could actually see this event for a much longer time, which gives you time to triangulate, to understand what happens, etc. So there is a challenge of having a wider window of observation. This is why there is this program to go to space. But at the cost of the mission, then it's better to go to very, very low frequency, because then the physics, again, is much richer and very different from what you can expect from the ground-based detectors. And to go at lower frequency with the existing technology will be limited by seismic noise and by other noise that I will talk about later on. So this is why we say, but why don't we bother with free-falling objects that are mechanical objects that we don't want to see free-falling? Whereas atoms are very nice. They accept to free fall and then to be recaptured with no harm. I mean, no atoms is harm in our experiments. So we should try to use atoms because they are perfect free-falling inertial frame references. And then we can apply the same idea. I mean, as I said before, what are we doing with an atom interferometer? We are basically measuring the phase of the laser at the position of my atoms, or basically measuring how the phase varies over time, the second derivative of this variation at the position of my sensor. So I could replace my mirrors by matter wave sensors. And then at 3 different points, I could measure how the phase is changing, the second derivative of the phase is changing, how the acceleration or the effective acceleration that my atom will see, either it's an actual acceleration coming from actual forces or an acceleration that comes from the contraction of space-time can actually be seen with this system. So this is one aspect that we want to use with this type of sensors. There are many more things that you can do with that with respect to, because if you can start to measure unknown forces on one hand, or if you can start to measure perturbation of space-time on the other hand, and they look alike, the signature is the same. So the only difference will be spatial frequency signature or time frequency signature. But you can then think of using that for detecting dark energy or dark matter. And these are some papers where they tried to explore whether the coupling from some dark matter model and dark energy model with atoms or with the light in such a structure can actually help you to. So that's usually, in this case, what you usually do is exclusion graphs. You know, you're measuring 0 with a certain precision, and then you know if you're sufficiently precise that this model works or does not work to a certain extent. Unless we have, well, maybe someone in the audience has a great idea of something we can actually measure. That's usually how we do. But still, it's interesting, or trying to push further and further until we actually see something which will be the signature. We expect to have space-time signature of dark matter or dark energy, because since the Earth is moving, then it's moving with respect to a mass distribution. And the same way we could actually look at some underground distribution, we could actually have a special signature, because at some point your instrument will be aligned and then in quadrature with the direction of the distribution, if the distribution is not uniform, and etc. So there are many, many open questions. There are models, you can put models, and then you can motivate some test of these models with these systems. Okay, so let me go back to Earth. So I want to do this experiment on ground. I want to go to lower frequency. And then I'm back to what I showed before, is the fact that Earth is a mess. And there is all kind of noise from the guy who will be working near the instrument, from the roads not very far away, to the earthquake on the other side of Earth. All this will actually create some background noise on your system. And it's even worse than that. If you look at all the noise, even the cloud passing by, the change of pressure will actually change the pressure on the crust, and then it will change the height of the crust. And even if it's by a micron, then it's also an equivalent. It's not a negligible signature of gravity that you will see. So everything will actually look like a gravitational wave if you are not able to distinguish. And that's what we call, in this field, the Newtonian noise, or the gravity gradient noise. So that's all the noise that comes from the variation of the mass distribution around your instrument. And at low frequency, basically any mass fluctuation has about the same amplitude, if you calculate that. So which means that now, if you just use 2 points, like a gradiometer, there is no way you will make a difference between something flying close that will have the signature with about the same frequency, and some gravitational wave coming from 2 black holes very far away that will also do the same variation, only if you have 2 points. But now the difference is, as I showed before, if now I have more points where I measure, far away happens something, and you can consider that the gravitational wave is like a spherical wave because it's a point source. So it's almost a plane wave on the Earth because it's very, very small compared to the distance, so that the variation over the length of your instrument will be uniform. Whereas any other small variations from the distribution close to your instrument will have a point source signature, as I showed before. So that's what we want to do, is we want to have some correlations that will allow us to spatially resolve the noise and then discriminate between the noise and the matter wave and the gravitational wave passing by. So this is what we have looked at by like thinking of building an array of quantum sensors, all interrogating with the same laser. So it's a correlated array of quantum sensors. And by doing that, if you make the proper calculation, you find out that indeed you can plug in some models of the noise that you know exist. And they call two types of noise. They call some seismic noise coming from the earthquakes and infrasound noise coming from the pressure variations. And if you plug this in, and if you look at your correlation that you can achieve, and you put some very optimistic numbers about what you can achieve if you had an infinite amount of money for your instrument, you can actually build a very nice detector that will make the difference between what is the contribution of Earth and what is the contribution of deep space. So the same instrument will actually give you information about the ground and give you information about the space. So that's a motivation. So motivated by that, we are currently finishing up to build an instrument underground. We started that about 9 years ago under a mountain in a site that was initially meant to launch some nuclear missiles, and is now free of use, so we could use it for nicer science. Yeah, so this is the place. Huh? So this is the Plateau d'Albion. That was the tactical nuclear defense, strategic nuclear defense for France. So you had like a few silos over there, I don't know, 20. And then underground, there were the guy who had the access of the red button in order to launch the thing. So it was super secured, and it's actually one of the best places in terms of magnetic, seismic, and temperature noise in the world. I mean, it's the best laboratory you can find. There is nobody around because it was a secret military place. So there is no noise, no, like if you take some other underground laboratory, sometimes they are very close to a highway, but this one, there is no highway. So it's very nice with respect to that. And we have drilled some galleries there, so I did not do it. But this is where so we have two arms like that, 500 meters on the ground. They are 150 meters long, and in that we will assemble some vacuum tubes to make our interferometers. What we could do with that is really, go from theory to experiment, but not in quantum physics, in geophysics. Actually, we've done that. We have currently measured the noise. So this is this is the background noise in our laboratory here, the seismic noise. So we had a network of seismometers, and we looked at what is the seismic noise, and we correlated that with everything that happens around. And so that's the first time it has ever been done actually properly underground. Even for the gravitational wave detector, so far they started to do that, but they have not done it completely. And we really compare that here. We are fitting perfectly the models, and we are in the lowest level of the uncertainty level of the model. So it's really a quiet place with that. And what's interesting is when you have that, we can then extract information about how we can correlate this information. And this is this sensitivity curve here that we theoretically calculated, where you find that once we have even the small version, 150 meters, we can start to measure this noise, or be sensitive to the noise. And if we can start to be sensitive to this noise, that means that we can extract the information. And that's what we want to look at. Okay, just to finish, some pictures about this instrument, because it's, I guess it's a scale that we are not so much used to play with in our laboratory. So this is like a small part of the tube here. It's only 6 meters. So we have 150 meters. So we have many tubes like that. So if you want some vacation on the ground with some very nice physical activity, which is bolting together many tubes, I'm happy to invite you for the next couple of months. But it's a very nice place. And yes, so this is a picture of for example, how it will be mounted. Here you see this is a prototype that we have in Bordeaux, where you have here the vacuum tube, and here it's plugged under the vacuum tube right there. You have an atom interferometer with the mot and everything and all the heads there. And just to finish with that, and then I will stop. These are some first results of the interferometer fringes that we are looking at. So we are trying to do this. So they are not great fringes so far, but that was the first one we obtained with this system. So here what we do is we change the interferometer time. So you expect the fringe to actually accelerate rotating. So we tilt a little bit. We're sensitive to gravity. We're looking at that. Not to enter into the detail, here you have many different colors. That's because we are using larger and larger area for our interferometer, using what we call the multiple, like instead of using one photon, we use more than one photon to create the beam splitter. So they are bigger beam splitter. And this works, and this is work going on. And I will stop there today and continue tomorrow then.
Thank you very much. It was very interesting. So maybe a couple of questions. Yeah.
I think there will be two, maybe one on the top, one on the bottom. It's a big radiometer. So one big difference is one is vertical and the other one is horizontal. There is some interesting aspect in vertical. Is you can have long interrogation times and everything. Here it's a little bit more technical. On the other hand, here we can really, I mean, at the end we want to have more than 1D geometry. So and you cannot be only vertical if you want more than 1D geometry. So this is an interesting aspect to look at horizontal. I did not mention that the gallery we drilled is really horizontal. So we really took care of having it perfectly horizontal. So that's one difference. The interrogation is a little bit different, and that gives access to other capacities for measurement. For instance, with this system, we can also, so that's something we're starting to explore, but we can also be sensitive to rotation. And so we can do rotational seismology. This is very new. But where instead of looking at how it shakes like that, you can look at how it wobbles. And that also gives you lots of information. As an example, maybe you know, maybe you don't know, but each earthquake is changing a little bit the axis of rotation of the Earth, and then it relaxes to its current axis of rotation. So the rotation is also actually a seismic effect on Earth that we don't know very well. Yes, so the redshift is for the clocks. Yes, but then you need to change. So the redshift, for the redshift, you go for a different height. So you change your gravitational potential, and then you look at distortion of space-time, like which is the time dilation in this case, due to this change of gravitational potential. Yeah, and basically, there are also proposals to do similar experiment like this one, but using clocks. And in this case, it's like the clocks is basically defining the time at a certain position, and then the interferometer, the light between the two clocks is actually, then you measure the time the light travel. In our case, we just compare the phase, so it's a little bit different, but it's also interesting. Well, you know, it's the thing is you can only compare what you actually measure because otherwise you can put any type of numbers. But if you want an actual measurement and an actual number, is an optical clock at 10 to the minus 18 can look at difference of the geopotential. Okay, so you change height, you change the gravitational potential, and this change has an effect on the time dilation that you can measure with a 10 to the minus 18 clock, so like an optical clock. And the change of height, the equivalent change of height is of the order of a centimeter. So it's here we are at about or better than that with the current technology, the current sensitivity we can achieve with our sensors. So because we're not measuring the same thing, a 10 to the minus 18 in a clock translates into 10 to the minus 9 for an accelerometer and so on. So we are similar, but we are not measuring the same thing. So it's
Are there other questions? Okay. So if not, we meet again tomorrow morning
Yes.
at 9. Thanks again. Thank you very much.